All right, afternoon, morning if you're joining from the US. I'll get started in a minute. So the format and the way I'm going to run this is I've got basically, see on the left, I've got a terminal open and I'll be kind of copying and running some of the commands we'll see in the tutorial. If text is too small and you can't see things, let me know and I can increase the size of either of these windows a little bit. And we'll kind of edit things as we're going along, try out some of the commands, run things, and see what's happening as we try different bits and pieces of this. So just as I say, let me know if you can't see commands and things like that as they're being typed, or if things aren't kind of clear as I'm working through it. We'll get started in a minute or two, and we'll work through this, and we'll get to the point where we start to build a little script and analyze some of the reconstruction output from the ESE recon. Okay, so let's get started working through a little bit. Hopefully the setup is all done already. Just a few bits and pieces here. We will need a file to kind of analyze and look at a little bit later, so we'll talk about that as the first part in terms of how we can grab that. If you've got it already, great. We don't need to worry about that so much. And a kind of few extra little notes here at the bottom as well. That we will need ESE shell set up for some of this, but only really to download files. We can do a lot of the analysis outside of that, and in fact, that might actually be the recommended way to do it, depending upon your particular setup. But generally speaking, there's going to be two ways in which we can do this. If you have ESE shell running locally, so not on the JLab form, as I'll have in a second, you'll be fine just to run things within the shell and analyze that. You won't have the full versioning issues and stuff like that. But the other version is just to have some working version of root on your local machine, which is what I'll be doing for the actual browsing of the files and running analysis scripts a little bit later on, simply because I don't want to pipe a bunch of windows from the JLab form as we're running this. It'd just be a laggy mess, basically. So just a kind of quick heads up as those are the two things. And that generally speaking, we're not really going to make that much use of ESE shell itself, other than the fact it has a bunch of stuff pre-installed like root and various Python packages and stuff like that. Okay, so with that out of the way, kind of quick introduction. Today we're going to be looking at analyzing the output of reconstruction from the simulation production campaign. So just a few words on that. We'll talk about this a little bit later when there's a small section on the full analysis chain. Generally speaking, the kinds of files that we might be concerned about from ESE software are outputs from the simulation and outputs from the reconstruction. So just to break that down a little bit, I'm going to take a look at some of the files from simulation campaign and just browse what's there and grab something. Typically speaking, there are three main things people are concerned about. And to some extent, some of this might just be input you provide. But the three broad classes that are stored in the file systems we're going to look at in a second are event generation files. So basically, this is some input physics events. So for example, if you're wanting to see if a particular process is possible at the IC, maybe you come along with some event generator, you create some events, 1,000 events of some particular channel, and you feed them in as input into the simulation. So one of the files that's stored there is just those input HepMC files, so that you could look back and maybe there's a problem way further down the line, which is actually just something to do with the initial input, which is why they're stored, and that users can basically come and provide the input there as well. So those are stored there. I'll not talk too much about that because that's really dependent upon if you're looking at some particular analysis, some particular channel. It's really up to whatever you're interested in terms of how you provide that. But typically speaking, that's just some HepMC text file. So basically some just file with a bunch of events. The recording will be on YouTube. We're going to hope to have that out early next week. It'll probably take a little bit, but expecting hopefully by Monday or Tuesday it should be there, the recording for this. So yeah, no problem. So the next thing, of course, is once you take that input file, first step in terms of, we follow through this chain of analyses that we'll look at later, you would take your input and you would feed it into the simulation. So in DD4HEP, you run that with particular detector geometry and you get some output. You have some simulated output, which is relatively raw information, literally just, per cell of a detector, some hits, some energy deposit in that thing, not reconstructed tracks or clusters, which is where the next part of this comes in and is what we're really going to be focusing on today. This is the output of the reconstruction, EIC recon, which is where basically that simulation output is fed in, and then reconstruction algorithms will work their magic and say, okay, this collection of hits here, I'm going to treat that as a cluster, and it's a cluster of some energy, applying some calibration and stuff like that, to convert that from some low-level energy into, maybe folding in the effects of something like a sampling fraction and spitting out at the end. It's a cluster with some energy, or it's a charge track or something like that. And that's what we'll be looking at in the next bit of the tutorial. So those are all three broad categories. And they're kind of organized in these file systems like this, where, for example, see in a second, you would go into, for example, the reconstruction directory, and then within that, they're organized by simulation campaign. So these are basically just nothing kind of crazy here. It's not no version 24. This is very much just year, month, and then version of it there. So this is the April 2024, for example, would be 24040. That might be a second run. That might be 24041 or something like that. But typically speaking, they're organized like that. Then within that, they're arranged by detector configuration, see in a second, and then physics process, which might have then lots of sub things within it, as we'll see when we're browsing this. So to take a look what's actually available, we could just jump on the website here that has it all outlined. You can take a look at what's there, the kind of structure of that and the number per thing. But if we wanted to actually look at the files themselves, we can dive straight in two different ways. So we're going to quickly look at each of those. And both of those are going to need us to use EIC shell. So I say this is the only real part of this where we need to use it or care about it particularly. I'm running it on the JLab iForm. So yeah, just running EIC shell in this directory. We're inside. We have this message pop up. This basically is sort of indication that we're there, and we can start running some of these commands. So we're going to jump into this file server, the xrootd file server, and see what's there in terms of different files. So much like a regular terminal, we can start doing stuff like ls, see what's in there. Ls EIC2. We've got, as mentioned, we see then now quickly our three main categories. There's some other stuff here, tutorials, other bits and pieces, but the main thing, of course, that we have our reconstruction directory, our full simulation, and our event generation files there as well. So we could dive into those. Say we wanted to find a particular input FMC file or something like that, we could go and try and find it. But expanding upon that, jumping into the reconstruction one, we see that, as mentioned, we have a bunch of different simulation campaigns. So basically just back from October 2022 all the way to the most recent one here, August 2024. And we can take a look inside there and see what we have. And we'll see basically, as mentioned, we're going to be a bunch of different physics processes mentioned. Not dumping that straight over the top of the hole. Sorry, first we have our single choice in this case of detector configuration, where we just have the latest, well, in this case, just ePIC Crater Lake version. And then here we have all of our different physics processes. So we could go ahead, pick our favorite, browse what's there, and see what we have. And as I said, depending upon the physics process, I mean, we just jump in, for example, the year. This is basically at this point sorted by different processes. Deep exclusive meson production, DVCS, other stuff here. Within each of those, there'll be some variety of different configurations, I'm sure. For example, if we look at DEM, or different beam energy combinations, different mesons produced, stuff like that, but we can dive in and take a look. For the purposes of this tutorial, though, we're going to be looking at a DIS channel. So I'm going to scroll down just to get half of that down here. So back one step. We're going to be looking at this neutral current DIS channel, where in this particular case, we're looking at this BeamNG configuration as well. So if we step back, we'd see that basically we have various choices: charge current, neutral current, different BeamNG combinations, stuff like that. And if you want to play around with this and compare different BeamNGs after the tutorial, feel free to take a step back and see which ones we've got here. So kind of free standard BeamNG configurations we could run: 5 and 41, 10 on 100, and 18 on 275, sitting there as well. So if we wanted to copy a particular file, though, let's go back to this point. I'm also going to put in that min q squared. So you see there's different minimum q squared values specified here as well. And in this case, luckily, that's the last step. Coming a kind of a lot of different options and folders deep at this point. But finally, when we do that, we see that we have this huge number of root files there we could grab. So lots of different ones. But at this point, I'm just going to exit this. We could grab one of these files. Don't happen to have this one copied, so I'm just going to do this as an example. And we can just follow this command here and plug in our particular file that we want to copy. Let's see, that one. I'm just going to do // which is just saying it just is going to copy it to the folder we're in now. There we go. It's copied that particular file. Do an ls. You see sitting at the bottom is that VIS file from that particular simulation campaign. So if you haven't already done so, recommend you try and grab a file from this directory now for analysis in the next part. If you can't use xrootd, there's a different way we're going to quickly look at as well. Some setup is required to it. Luckily, I've already got this sorted on this, at least it was this morning. So I'm just going to do this final command here. Again, you can browse all the different simulation campaign outputs using this thing. As mentioned, though, if you don't have this set up already, there's various bits of setup we need to do here. This credential here, you need to grab from the information for the Mattermost page. So if you go to the Mattermost page, go to View Info, and then click More here, you'll see the two credentials you need there basically to get that to work. So you can go ahead and grab those, plug it in. I'll not reveal them in this one, but they're sitting there if you need them. And once you have that set up, again, you can just run it like I've just done there, and you can browse around in that hot's content. So again, I'm going to that, and again, we have ePIC, Radar Lake, stuff like that. Dive in, see the files up there. So again, this time jumping into that particular folder, we see there are different options, and eventually, if we keep going through them, we'll hopefully find some root files that we could copy out if needed as well. If we want to copy a file in this case, I'm just going to say, let's copy this one. Instead of doing ls, we'll just do mccp, give it the path. I'm going to have to modify that to be s3/eic test. And again, we can copy over the file. So they're all roughly about 80 megabytes. So even if you're copying them to your own system, shouldn't take too long. And now we have, again, that one there in our folder as well now that we've copied it. So nice and straightforward. Just basically, at this point, use whichever one you want. I would add that this S3 is eventually going to be removed. In fact, you can kind of even see that in the sense that we don't have the August simulation campaign here. Going forward, xrootd is going to be the only place these files are. So, in fact, this might get removed going forward in the tutorial. But for now, you can use it to grab files, and it might be something you prefer if, for example, xrootd or whatever isn't working for some particular reason. Still a bit of time to try and get it set up. Okay, last little comment. I'm kind of in a vacuum, maybe doesn't make so much sense since we haven't started looking at root scripts or anything like that yet. Rather than copying the files, if we're running inside the eIC shell, you don't really need to actually copy them anywhere. They're sitting on the server. We could just tell our script, go and open the file from this server. It's sitting there, it can access it if you're in eIC shell. So you can just tell it, go and access that thing, and we can just analyze the file directly like that. So if you're doing the second option from before, though, in terms of setup, and you want to copy this to your local machine, of course, you're going to have to download it first. So you can't really do that, but just something to keep in mind. So yeah, as a quick reminder, for the next step, just make sure effectively just when you're in eIC shell, it doesn't need to be this specific file. You could grab, whatever number, 00023, whatever your favorite number is. Just copy that and make sure you can kind of open it and run it basically wherever you've copied it to. So before we move on to the next thing, just a quick note, kind of an obvious question you might wonder is, okay, well, grabbing one file is all very well. What if I want to grab a whole bunch? Normally, of course, you might just use a wildcard, copy file, because as you can see, all of these have a very similar naming convention, just this last digit changing. Need to use a few little tricks with that. So there's just some examples of how you can do that using both S3 and XRootD if you wanted to do that. Again, something you might want to do if you say happy with your analysis script and want to run it on a whole bunch of files. You might just want to grab them all and move them somewhere and run it on them. So you can do that, and there's just some quick examples of work that as well. I'll not run through that at this point, but that's there to take a look at if that's something you eventually want to do. So yeah, key takeaways. Yeah, focus really on these if you can. If for some reason there's an error of that, try and work it out at some point. But for now, the mini.io client and S3 server works okay as well. It just doesn't have the very latest simulation campaign there and won't going forward as well. And also, if you're in eIC shell, you can just stream these files directly and don't, strictly speaking, need to copy them anywhere before you run anything. Okay, so now that we're done with this part, as mentioned, this kind of is all we need eIC shell with to some extent, as long as we have some newish version of root that we can use. So the next part of this tutorial, we're going to be looking basically at the file we just copied, which in this case I've already copied to my local system. On this directory though, you have it sitting there. So it's very long file name, pip8 ncdis thing sitting here. We're going to open that and we're going to take a little bit of a look at it in just a second. So what we're calling the output here is those reconstruction outputs from something which has been processed through eIC recon. A lot of the stuff we're going to see inside this file are the branches and leaves of something which has been produced by eIC recon. So one thing I would say is that if you're kind of curious as to, where has this particular bit of information come from, the answer is almost certainly that some algorithm or factory within eIC recon has created it in some way. That's a little bit beyond the scope of this tutorial, but if you want to kind of dive into it, I would highly recommend that, once you've had a play around with the file, had a look at it and done some of the rest of this tutorial, take a look at eIC recon and start trying to track down, well, okay, for this particular thing, pick your favorite detector, for example. Maybe it's some calorimeter clusters, and start taking a look at, okay, well, which factory or which algorithm is producing that in eIC recon? Because one thing you might feasibly want to do, say you're not seeing what you expect for your physics channel, it might be a case that you actually need to dive in and start maybe modifying one of those algorithms or factories and changing some parameters of that to try and get things with the correct efficiency or resolution. But going forward, we're basically going to be jumping into this with root. As a kind of word of warning, if you're using an older version of root, so something older than 630, when you open the file, you might see slightly strange behavior, which I'll kind of explain as we're browsing it. It'll also give you a lot of errors, which it will still open, but will complain about things, and it will be a bit of a problem. So if you have a newer version of root that's much better, and eIC shell now has root 630 and doesn't have this issue. And of course, if you're doing this via some sort of exporting, things are going to be slow if you're trying to kind of draw interactive windows and stuff like that. So just a kind of word of warning of that. And you can also, as well as a link here, this web viewer, you can open the file of that. Just it's a bit more limited in terms of what you can do. with it, but you can still browse the tree and see what's in there and stuff like that. Okay, so we're going to open this. I'm just going to open it by just saying, root and file. Got a bunch of warnings about it. Complaining about some dictionaries, nothing fatal. I'm just going to open the file. So I'm going to open a T browser, and that's going to let me just open the file and start looking through it. And we see that in here we have some events tree. And we're going to look at that and start browsing through this and see what we have available. So the weird behavior with all the versions of root is basically that if you do this, if you open the file and open it with a T browser, nothing will look particularly weird until now, except as you're starting to look through this and maybe starting to, double click on some of these things and draw some plot like this, it will just start deleting them in the browser as you're looking at it. So not particularly helpful. I am a bit annoyed that it's so incompatible with all the versions, but it is what it is. And just as a kind of word of warning, if you start seeing that and you had a bunch of different warnings as you open the file, it's probably a root versioning issue that's happening. But in terms of this file, we have, as you can see, an absolute ton of different things in here. Keep scrolling for quite a while and just have lots of different branches, lots of different leaves with lots of information in the file pertaining to effectively different detector subsystems. Most of them are quite self-explanatory. So, for example, we have H-cal barrel clusters, hadron calorimeter barrel clusters from the reconstruction, and then the variables within that again, pretty self-explanatory. H-cal barrel clusters.energy. We would assume that's probably the energy of the clusters for all of the events. We get something there we can have a look. Position X, Y, Z, again, relatively straightforward. We can kind of guess what that might be. There's so much stuff here, though, that finding a particular thing might be a bit of a challenge. So what I would recommend is using this little tool at the top, this little funnel symbol in the top left. If we click this, we'll see the minute it just has a star, basically a wildcard, and we could type something in here and then end it with another wildcard, and it will just leave us with the branches that have that as a matching name. So for example, we can see it there, so it's a bit obvious, but say for example, we know we only want to look at some stuff from the B0. So I'm just going to plug in there B0 star, hit enter, and now we're just left with, rather than that huge list of things trying to hunt through, we just have things that match B0, and we can just say, okay, actually, let's look at the clusters for that, say, and let's look at our energy in the B0 calorimeter. Oh, there we go. We have some plot there of the stuff. A kind of quick word of caution with this, though, if we want to get rid of that, we click on this now, it has that set. But if I do that, just go back to that, it's still stuck with just these things. The problem is basically you need to go back, click on the events, and then get rid of it. Now we get everything back. So we have a lot of stuff to look through. We do have an exercise. But before we get to that, I want to talk a little bit more about how we can kind of plot some stuff from this, take a closer look at it and extract some information. And to do that, I'm just going to quickly go to open the B0. I'm going to look at the Monte Carlo particles branch because that's going to have some information we can quickly take a look at. So again, I've just filtered it such that I only want things that have a name matching MC, Monte Carlo. Basically, this is just a branch. This one I've selected MC particles. This is just a branch which contains all of the truth level information on an event by event basis for our particular reaction. So for example, we could look at the PDG values of the particles and events. So I'm going to go ahead and double click on that, and we'll see that the browser is nicely generated some histogram, but there's something a bit annoying about it in the sense that, let's face it, it isn't actually particularly useful. PDG codes, it's drawn off our axes out to 20-odd thousand, 22,500 this side, minus 22,500 that side. But most of our data is bunched up here. And it's also decided, basically, as we've done this, what it's done is basically taken this branch and it's defined and filled this histogram on the fly as it does it. But it's done so with some fixed number of bins. And as a consequence, unfortunately, we say, for example, want to know, oh, well, what's this? we don't really actually know. It's, binned it too coarsely and just grouped all of this stuff together. Again, all we can say here is we have, some number of particles with PDG code between 0 and minus 4 something, 440, and equally something between 0 and 440 on the other side. Not particularly amazing. Basically, that's going to mean all of our, for example, pions, which have a PDG code of 211, they're going to be smushed together with muons, electrons, positrons, all sorts of stuff sitting in there, right? So not great and not that informative. So how could we get around this? The answer is basically that we can define things a bit ourselves. And we're going to basically interactively draw some stuff directly from this tree. So we can do that using this ttree draw command. We're basically going to say from the events tree, draw this quantity. Not going to draw PDG just yet, but I'm going to draw this other thing instead. So we could just go ahead and we're going to just feed this an argument, which is a particular branch there. We see that we have MC particles, dot momentum, dot Z, which is something which sits here. So we go ahead and do that. If you don't have a T browser, it will just make and fill a canvas, by the way, as well. We'll go ahead and do that. And you see it's drawn this histogram for us of the Z component of the momentum for all Monte Carlo particles. So quite useful. Again, though, it has this problem where it's automatically scaled this. It's automatically just decided, okay, I'll draw that and I'll fit the stuff that's there within some number of bins. Can't remember off the top of my head the auto binning numbers, a couple of hundred, I think maybe 200 or something like that. But again, might be too coarse for what we need. So for example, we're spanning this range of 0 to somewhere around 280, maybe makes sense given that we're looking at 18 on 275 events. And equally going the other direction, we have 0 to roughly minus 20, so on this side as well. So again, the electron has 18 GeV, that's going in the negative Z direction, protons going in the positive Z. So maybe this actually makes some sort of sense in terms of where we're seeing things. But unfortunately, for example, though, we wanted to look at the stuff going in the negative Z direction. Again, that binning is a bit coarse. It's kind of smushed everything together a bit, and we might want a bit more detail than that. But luckily, we can improve on that, because when we do this command of ttree draw, we could tell it that as we do so, actually, I want to define this histogram H1, and I want a certain bin range. So let's actually say we want to do that. Let's just look at those negative momentum particles. I'm going to say I want 200 bins between minus 20 and 0 for this quantity. Go ahead and do that. And now we see we have something which is a bit finer in terms of the binning there. We have some big spike towards the end at negative 18 or so. Again, maybe makes sense given that some of our beam particles will have that momentum basically. And then some spread between 0 and 18, which before was lost in the coarseness of the binning that it's done automatically. So I'm going to rebin this slightly. I'm going to span a slightly bigger range. I'm going to say let's draw all the way from there to there with a bit finer binning than before. And again, we can go ahead and do that quite quickly on the fly. So it's a nice and easy tool that lets us kind of just, if something isn't displaying correctly when we're browsing it, for example, our PDG code, we'll go back to that in a second and make it a bit more sensible. We can just draw on the fly these things. But it's also a little bit more powerful than that, in the sense that we can also apply cut splits. We can apply event selection as we fill the histogram on the fly. So as a quick example here, we're filling that previous histogram, the one we just saw, the 360 bins between minus 60 and 300, with the Z momentum of the particles. But we're going to require that for the things that go into the histogram, we're only going to draw the ones which also have a negative charge for that particular particle. So it's going to do this basically as it's going through. For every event, it's going to look at the particles that are in the event. It's going to look at the value of their charge. If it's negative, it's going to fill the histogram. If it's positive, it's just going to skip to the next particle in that event. Go ahead and do that. See, this time, our histogram looks quite a bit different, where we don't have that spike at 275, which if we're saying that's probably from the beam protons, makes a lot of sense. They'll be positively charged. Instead, we're just left with our spike at negative 18 and also a peak sort of sitting around 0 there as well. So some stuff we're producing around 0 in terms of Z. And it's not just one cut, we could keep applying different cuts as well if we want. So we could say, give me the stuff that's negatively charged and also has a mass greater than 1. So let's get rid of basically, if our hypothesis is that these are beam electrons, their mass is going to be less than 1. So if we require a mass greater than 1, that spike presumably is going to vanish as we do this. So let's see if that's correct. Go ahead and do that, and yeah, we see that straight away. We get rid of that spike at -18, and we're left with this tail of stuff. We now have 4 fewer events, but nonetheless, we've kind of selected out this particular range of stuff and got rid of those electrons. So we can also give this drawing options. So for example, we could draw it with errors on the histogram. See there's some sort of fuzz basically on this. There's little spikes at the end of these. That's basically our error bars sitting on top of each of those there as well. So we can draw it like that as well if we want. And finally, we can also do 2D drawing as well. Let me play around with this in a second. But basically, we could provide it with that and say, okay, actually, I want to draw, in this case, the Z momentum versus the charge of these particles and see what we get. The binning of this is a bit weird to notice that the way this is written is that we have Z momentum, then the charge, but in terms of the binning, it's the second one of those that's the x-axis, and the first one that's the y-axis, which is slightly strange. So this is actually our binning in the charge, and then the binning in the momentum. We'll go ahead and do that. I control that. Again, I'm providing this argument col Z. That's just going to make sure it draws in color with a Z scale. We have a slightly strange looking plot, but basically we have some bands for different discrete values of the charge, and we're seeing bands of stuff. So interestingly, we're seeing fractionally charged stuff. So we assume basically partons or something it's keeping track of in there. We could also start doing maybe cuts and stuff like stable particles and stuff like that. We might get rid of like that. Okay, so as a final thing, I mean, I mentioned this. I'm going to go way back to our first thing through us on this was that I said that PDG isn't exactly useful. So I'm going to say, draw me the PDG, these empty particles. This time, give me 4,000, 5,000 bins. Now when we do it much finer binning, and we can actually start to see if we zoomed in on this, we could actually pick out a particular PDG codes. So for example, 211, this sort of range, these are pions and stuff like that. So we can start zooming in and selecting those and saying, okay, that's that particle. And if we wanted, for example, in terms of these cuts, rather than saying we want things of this charge and this mass, we could say we want ones of a specific PDG code or something like that. Okay, so that's just a kind of quick run through and a quick example of that. Back to the exercise though. Given all of that and given some of the sort of pointers there, the quick task is for you to take 5 or 10 minutes just to kind of explore the tree, take a look at what's there, and in particular, try and find something to do with this end cap, the ecal end cap, and try and make a plot of the negative end cap ecal and see what you get for that. So whether you kind of find that and draw it interactively in the T browser, or you just find the name of it and then do a T-tree draw, fill some custom histogram, up to you. But try and find that quantity, plot it, and see what we get. And in particular, see if you can kind of spot within that a peak from the scattered electron there as well. So I'll give you 5 minutes or so, 5 or 10 minutes to do that. And when you get something, feel free to just put it in the Mattermost. So you'll see from this morning, there were some plots from people in the tutorial this morning showing what maybe you'll end up with. Cheating, I guess, a bit in the sense that they've got the name of the thing you're looking for. But you can go ahead and try and find that in the tree, identify it, and make your own plot. Again, maybe try and zoom in or rebin it in a different way, stuff like that. So I'll give you 5 minutes, and what I'm going to do this time is I'm going to stop sharing the screen so that's not too distracting. If you're sitting there trying to kind of browse through the tree yourself, we'll come back to this in 5 minutes or so and take a little bit of a look. I should add as well, yeah, if you have any questions or get stuck on anything, please just feel free to either post it in the chat or on the Mattermost. And I'll try and keep an eye on both and answer things as I see them. Starting to get some plots in there now. So yeah, we've got the nice on with a log scale there as well. I've got the energy of them, yeah. P okay. Give people another minute or two to keep kind of browsing around, make a plot. I'll try and get a plot of that. And just exploring the tree a little bit as well. A few kind of last few comments to make on this, and then we'll move on to our next section, which is really kind of turning this into an analysis script and seeing what we can do with that. All right, so if you're kind of still browsing through, making a plot, yeah, say just feel free to kind of add it there as we go along. Because I feel just a few kind of last comments on this as we kind of work our way towards the next section. So again, yeah, stop sharing my screen. Sorry. First thing, as I say, just given the sheer number, no need to look at a laggy video of myself there. One of the first things I would probably do in terms of trying to find this and trying to find those end caps is again just using that filter tool, just because the sheer number of different branches and trees we have here. Go in and go with that filter, plug something in like that. Just reduce it down to just stuff which has the word end in it. Probably a good start. We would assume that information to the end cap includes that, or at least we'd hope so. So we can plug that in, see what we get, and see, okay, there's still a lot of stuff here. We have, for example, end cap, end clusters, end cap, end raw hits, and stuff like that. Since we're looking for clusters, we could even put something, a wildcard to do with clusters in there as well. But also we want negative end cap cluster, so this is probably the one we want. We can start plotting something from that. Okay, last few things. I'm going to get rid of this and we're going to go back to our Monte Carlo particles. This branch here that we looked at, we'll be coming back to this in the next step. As mentioned, this just contains all the information on the truth particles. In reality, of course, when it gets to the point where the EIC is running and producing data, we don't have the equivalent of this. We don't have the actual truth sitting there. It'd be very nice, make our jobs a bit boring maybe. But in terms of simulating and producing analyses at this stage of things, this is very important and something we're going to be coming back to a lot, because a lot of the time we really want to compare things back to what we actually fed in as truth. So for example, in a physics analysis, say you're looking at the number of particular reactions you get, something like that, and you're looking at a particular kinematic range or something like that. You need to be confident that the events you end up with, and you say you've selected and identified for reconstruction, we need to make sure they actually have some bearing on the truth. We can reconstruct them and say, actually, these pretty much do correspond to what we originally fed in, and it makes some sense. Because if it doesn't, then it's basically telling us that what we've detected is just a load of junk, and isn't actually anything to do with what we fed in to begin with, which in itself might be interesting to know, but not usually the result we're hoping for with some sort of study. So there's a lot of information in these links at the end of this section. Might be something you want to kind of dive into and take a look. PDG code there, useful for kind of identifying what we're going to be seeing. See in the next section, we start to look at specific PDG codes when we're doing our cuts. But these two in particular, if you want to dive into this, I know some people are really interested in this sort of thing in terms of how they're structured and what's going on there. Not really necessary for just plotting stuff and understanding it, but if you want to take a look, it's there. The links are there to follow. And we'll be coming back to this branch quite a lot in the next section as well, where, for example, this contains a lot of information that we can utilize. So, for example, the actual PDG, and what particle was it to begin with, the generator status we'll be seeing in a second as well. Was it a stable particle or not, or was it just some sort of intermediate state or something like that? The vertex, everything like that. Very useful and important information. And again, just to reiterate, all of these branches that we're seeing here, all of the information we're accessing and plotting and taking a look at, all of these are populated basically through EIC Recon. It's taking that simulated data, it's reconstructing it and filling these according to some set of algorithms and factories and stuff like that. So once you've had a chance to kind of work through this tutorial and reconstruct things and take a look, even if you kind of already know you don't want to dive into modifying some of those algorithms, I'd still say it's kind of worth taking a look and trying to find out, well, okay, for this thing I'm looking at, where is that actually made? What is the process of that? How do I get from some collection of hits in the detector to some cluster? Or how do I get from some collection of hits to some track? Because that's what's really kind of happening with these algorithms. They're kind of grouping together hits and detectors and saying, okay, this thing's a cluster and this thing's a track from this set of points I have. And given the way it's curving, I think it's positively charged, negatively charged, it's this thing, so on. So worth taking a look and diving into that as well. But let's see, familiarize yourself with what's there first, maybe, and take a look in terms of what the output is. And this is something we're hoping to expand on in the near future, where maybe we can start to maybe have some sort of map where we can say, okay, well, these things correspond or come from these different factories and stuff like that. So the method we had here of kind of just going through and drawing stuff like this, great. We can make some little plots. We can draw things interactively. We can add cuts even, so it's quite powerful. But at the end of the day, we don't want to sit here and, type in 200 different draw commands with varying degrees of complexity, with hundreds of different cuts included and stuff like that to do our analysis. We can. I've spent an hour doing that for something once where I just didn't want to have to write something. I was just looking at something quickly from some data, go through, print stuff to screen. It's a very powerful little tool. But at the end of the day, more realistically, we're probably going to want to just have something, some little script or macro. We can just say, okay, when I've got the data, I just feed it the file and it will produce a set of plots that I want. And that's where kind of the meat of this comes in, which is analyzing this reconstruction output and writing some sort of macro or script we can use to analyze the trees using some of the tools we've just seen. So whilst it's useful, we're more realistically going to go ahead and do this. Kind of a few quick words on this before we dive in. The output we have here, the simulation output, they're very much designed to be quite transportable. So in that sense, they're sort of flat in the sense that there's nothing embedded within them. And we don't need some huge set of different packages or anything like that to handle output. If we produce the file via ePIC Recon, we can copy it somewhere else. And as long as we've got root, we can just open the file and take a look and see what we've got there. We don't need root and a million other different packages to open it and take a look, which is basically why we can, as we've seen here, take it from somewhere where we have, copy this. We're using eIC shell from that file directory. I moved it to my local machine here at York, and I'm just opening it and taking a look at it using root on my machine here. We don't need a separate set of packages or anything like that. You may know sometimes it can be a bit of a nightmare when systems don't manage to have a bunch of different packages installed. So saves all the hassle of that. So we're going to work through a sort of sample analysis. A quick caveat on this before we do. The way this is presented, there are 3 different approaches to this, which I think cover most of the kind of ways in which people would try and analyze a root file generally. The first is simply just using root itself, using root directly, using the T-tree reader, which basically is going to open up that tree, that events tree we saw, and then it's going to look through that event by event and do something with it. Nice and straightforward. Basically, if you're familiar with C, C++, will all look pretty straightforward. But I know these days a lot of people maybe aren't so familiar with that or looking to use different things. So as well as that, there's also Python-based version of this, which is sitting here, which uses a slightly different way to do this. Again, it's taking this root file and analyzing it. The result will get to the same, but just a different approach to doing this. So a little bit about that. The way this works, and the way I've presented this in terms of how I'm analyzing Python isn't pyroot, because that's basically root with a Python wrapper. This is using something called uproot, which basically takes our root tree, you load it in, and it will take the branches from that and then turn them into NumPy arrays. So you can manipulate that in a lot of ways, just using purely Pythonic sort of way approaches and methods. I'm not so familiar with that. So the way I presented this is looking at those in more of a root sort of way, where basically use uproot to turn these into arrays, loop over the arrays in a fairly root style way. So it's not the only way to do it, and it's just the way I'm kind of familiar with doing it, basically. So by all means, if you want to tackle it in a more sort of Pythonic way, where you're just manipulating NumPy arrays and doing stuff like that, go ahead. Basically, once you use uproot to select out the branches you want and convert them to arrays, you can play around with them in any kind of Pythonic style way you want, basically. But the example I present, as I say, is very, it's basically, if you look at them and compare them, the approach from the root T-tree reader and the uproot version are very similar, and the kind of logic they follow is quite similar as well. But yeah, feel free to do it in a quite different way, as long as it, again, works and is consistent. Really long a bit. And finally, there's something which is a bit newer, and something that was new to me. And again, I know this is becoming a bit more popular. It's something which has been added to root more recently, and that's using data frames. So again, you could turn it into data frames in Python, but in this case, root has something called an OR data frame already, where basically familiar with using R, this might be something you want to take a look at and try. This is definitely something people seem to be moving towards in some way. I did this for the very first time. We have an example here which Simon Gardner wrote me as a demonstration, and basically I took this and there's a kind of working output of this, which is the same as the root and the Python versions above. It gives the same output, but it's quite different how it behaves. So in this case, we're basically defining some data frames and filling some stuff with it. Again, if that's the way you want to approach it, great. Feel free. Go ahead. It's it can work. I'm personally not a huge fan of it. I found the kind of logic and the way of working with this very different to what I was used to, and I found a lot of the time what was actually happening with things here was being a bit obscured, and it wasn't so clear the logic as to what was happening and being applied. Whereas I think the way in which I present it is the root and the Python versions, the sequence you're working through is a bit clearer, at least to me. It might not be if you're familiar with R. It might be a mess looking at it in the sort of root version, and this maybe makes a lot of sense. So this is also a way in which you can do it. So we're going to look at some exercises though, and I think given the timing of the one this morning, we'll basically stick to one. We'll stick to the efficiency analysis. We'll take a look at it, and we'll work through it and see where we get with that. So up to you. I'll leave it up to you. I'll be looking through it in the root version of this. But if you know already you want to use the Python version of it or start in a sort of or data frame sort of way, feel free to take a look at that, start exploring that and playing around with that. I'm just going to work through the kind of the root version of it simply because it's easiest to work on my machine here, basically. So quite straightforward. Basically, we can just make a little file. It's just call something like track analysis. Floating around from earlier. Yeah. And just open up some new file using your favorite text editor and start plugging things in. So the blocks of code here are kind of written such that you can just grab them, copy paste them straight in and run them and basically build up bit by bit. So we'll maybe just talk through some of this, then we'll get to the exercise and talk about how to get kind of started on that and what we're going to want to try and get out of that as well. So pretty straightforward. This first block of code basically is just defining, we have some void function and it's given basically some string as one of the arguments to it, which is just, in this case, this path to simulation file. Just point that to the path to wherever your file we downloaded earlier is. And then after that, all it's doing in this case is defining some new file, which is called ofile for output file. It's opening it, recreating it, and at the minute it doesn't do anything. It just opens the file, writes nothing to it, and closes it. Great, but if you copy and paste this into a script, comment everything other than that in here. See that I'm not lying. So at the minute we have nothing in here called outhis.root, which is what we said our new file was going to be called. But I made my very basic little macro there. I can just run it with root backanalysis.c. I run that, and now we see it's made that blank file outhist.root. Of course, in reality, we're probably going to want to do a lot more with it, and the method we're going to utilize is a T-tree reader, where basically we're going to open up the in file we had, and we're going to set up a chain which will then read through that chain and go event by event through that, and do something with those things. So we see we have a chain. This tree in that file was called events, the one we care about. And I'm saying just add to that chain this file I've defined above, the input file we downloaded earlier, initialize it, and then I'm going to assign these T-tree readers. Basically, these are just things saying, in that tree, these are the things I care about. If I say I want, port gen start, that's going to be whatever this thing is. So in this case, I'm saying this is the branch in the tree, MC particles.generator status, MC particles.momentum x, and now I can access those as I read over this thing. So you just add what you need. We'll see in a second quite a lot more is needed, but add what we need, plug it in, and then we can start iterating over it. And this is where the main bit of the actual analysis goes on here. We have basically some while loop, which just says while we can keep breeding new entries in the tree, put the next one. And for every entry in there, for every event, look at the size of this particular branch. So basically, that's just going to tell us how many particles are in that particular event, basically. Loop over all of the particles, and assign some integer, which is their generator status, based upon the value of that for that particular particle in the event. At the minute, it doesn't actually do anything more with it. Again, we see the same thing for the momentum. Doesn't do anything more with it. But we could, for example, say, let's just print the screen. That. Now when we do it, we'll get a bunch of stuff printed to screen, basically, which is going to be the momentum of all of the individual particles in the event. We haven't added something to separate event by event. We don't know which is which. Could go and add that as a cout. Not especially useful, just to have a bunch of stuff dumped to screen, but just to show you that it's giving us the information. Okay, so in reality, though, we want to do a lot more than this. We want to start filling some different arrays. And what we want to actually do at the end of the day is try and get something out of this and do a little analysis. So the analysis we're going to do, kind of outline here. I'll quickly also say to kind of get set up rather than kind of writing this from scratch, I refer you basically to this. If you follow this link, it gives you a template. Again, you can copy paste it. Just make sure you change the pathing of the files, so the input file and the output file and stuff like that. Make sure it's something you can actually read and access, and make sure that it's going to write to somewhere you can write to basically as well. But what we're going to do is we're going to try and get the efficiency of the particles that we actually reconstruct as tracks for our event. So what we're going to do is start with trying to get the efficiency as a function of pseudo rapidity, as a function of eta. And we're going to do that by basically opening the file, looping over all of the events in the file. Within each of those events, we're going to try and identify all of the stable charged particles that were there in terms of the truth information. We're going to try and associate them with a track. We're going to try and say, okay, does that correspond to a track we actually detected or not? And then we're going to fill some histograms to try and determine the efficiency of this. So a lot more here. Basically, if you like, you can copy paste this and kind of add it to the script you had before. Or you can, not going to say cheat, but you can kind of skip the potential kind of stumbling points of that and just open the template. There are similar ones for Python and similar ones for the OR data frame as well in terms of getting started. So you can just grab that, again, plug these things in and check you can run it, which I'll show in a quick second as well. But we can see some of the basic logic of this here, which I'll maybe talk through, and I'll get to what the exercise is in a second. But we see basically that in addition to defining our branches, we had a bunch of things we're going to look at in our tree. We're also going to define some histograms that we're going to fill and then write at the end as well. So we're going to define some histogram. So th1d is just a 1D histogram in root. We're going to define a new one called part eta, and we're just going to say, and it just has its name, part eta, and it's going to have a title here and an x-axis title, which is just eta. We're going to have 100 bins between -5 and 5. And then similarly, we're going to have one. This is going to be the one for our particles which have a matching track. Again, same binning. And our strategy basically is that to get the efficiency, we're going to need to fill both of these and then divide them to get efficiency. So we just want to know all the ones that we actually detected, how many of them do we get compared to how many we actually threw, basically. So all the efficiency is detected, overthrown, basically. And we're also chucking in here as well. We're doing for the match particle tracks. What's the difference in R between the ones we actually detected and the ones we threw as well? Something which we might want to, for example, put a cut on. Maybe we say we want to make sure that the tracks we reconstruct pretty much are in the same position as the ones that we actually threw. Might be a sensible cut to apply. But the basic loop and the basic logic, though, as we said before, is just loop over all events. So again, keep reading through the events for each event, look at the Froome particles, the Monte Carlo particles, look at all the ones in that given event. In this case, we're adding this if condition, which is just some cut saying, if they're not a stable particle, keep going, don't bother looking at it. But if they are a stable particle, get the PDG code. And then once we have that, we have this other cut, which just says, if it's one of these 5 charged particles, keep processing. And then, as we see, we assign some momentum vector and then get some information from that. And we fill that first histogram there as well. We fill the value of pseudo-rapidity for the Monte Carlo particles. Gets a bit more involved here, where we do this association with the charged particles, where we use these associations and say, okay, if the track and the Monte Carlo particle associate with each other, in that case, fill this free vector with the matching track and calculate some stuff again and fill our histograms as well. So, as I say, if you go and grab in that exercise script repository, you go and grab those. Go to the one I did earlier. See, we have this efficiency analysis script. I'm going to quickly run that and we'll see what we get from it. And then we'll take a quick look at the actual script itself as well. If you run that, it'll take maybe a few seconds to process. Has some warnings, but it's run, great. And if we have a quick look in its directory, we see that it's made this output file sitting here as well, which as we can see is just made just now. And it isn't one I've made earlier, so we can open that and take a look. Well, in a second. So again, compared to the kind of stuff we had in that first one where we start copy paste things in, you see we defined a few of our readers where we're getting basically information from the MC particles branch, the reconstructed charged particles branch, and then this associations branch as well. Check if they actually match to a charge to a Froome track or not. Find some histograms. There's that big loop. And as you can see, I've commented this, so it says where each of these is closing. And we see here, I've commented this out. I've got at the end something which will give us our efficiency as well. So basically, I'm taking the histogram of the matched particles, dividing it by the one for all Froome particles, and looking at the result, basically. So we'll have a look at what we got, and then turn it over to you to kind of have a little bit of a play around with this and try and address some of the stuff in the exercise there as well. Have a look at this. Already know it, I've got 3 histograms in the air. I've got the value of the pseudo rapidity for all charged particles. We see running between -5 and 5. We have this big spike at 4 point something, at 4.2, 4.3. Some tail, some stuff here at -2 and a bit, and some spread between it. So a few things to think about as you're editing the different macros and scripts. For a start, is this range good? Something, maybe we want to change this a bit. In particular, it almost looks like we're cutting off tail or something here. Is that something we're worried about or we care about? Should we extend that a bit? Does the binning look okay? Does it make sense? But keep in mind that if we change this one, if we want to take a ratio, we need to make sure the binning of our 2 is equal, or else we're going to get nonsense out. Again, here we have the pseudo rapidity for charged particles that have a matching track here as well. So interestingly, we see that for the ones where we have a matching track, we don't have that big spike at the high pseudo rapidity. However, we do have this one down here at -2 and a bit or so. And also, finally, we have this plot here, which again, you might want to think about in terms of binning and modifying. We have this difference in the position between the matching Froome and reconstructed charged particles, so delta R between them. And we can see plot from 0 to 5, but we basically don't have anything beyond even 1.5. It barely looks like there's anything there. Maybe a bit of fuzz here. Zoom in and have a look. One event down there. But most of our stuff is bunched up over here. So is it a good binning range? Probably not. Something you might want to modify. In particular, maybe it's too fine in this particular case. but also clearly the range there is too big. I mean, yes, we can zoom and modify this, but if we were just going to draw this directly plot, maybe not the most useful thing for us to do. So I'm going to quickly show how we can get that. This quits. Great, it's not a big crash in the background. Quickly modify that efficiency analysis script. So as mentioned, maybe some of these aren't so sensible. It's going to change these slightly since we already know we had stuff extending a bit beyond that to show how high it goes, but definitely it looked like it was running higher than higher than 5. So I'm going to add this new histogram, which is the track efficiency as a function of eta. So going to make the title of that there. You can see here we define the x and y axis titles to this. It runs over the same range. So again, 120 bins between 0, -6 and 6, 120 bins between -6 and 6, both of these as well. And at the end, basically all I'm going to do is that once these are filled inside that loop, where I've gone through all of the events, I'm going to take the division of these two histograms. I'm going to do this argument b so that it actually counts the errors correctly. And when I run this time, no, not that, sorry. To run this, our output will hopefully look a bit different. We should have a new histogram there, which is just that efficiency at the end as well. What do you know? We do indeed have that. We have some efficiency histogram, maybe slightly misnamed axes, since this is running 0 to 1, not 0 to 100. Could scale that if we like. So that is indeed a percentage. But we see that from our plot, we have now basically our efficiency is a function of the pseudo rapidity across the detector. So what we see is maybe something not so surprising. And I guess a quick primer for colliders and talking about detectors and colliders, pseudo rapidity is effectively, this is proxy a lot of the time for the angle. Basically, it's in a log of an angle or tan of an angle, basically. So rather than talking about angle in terms of theta, often you talk about the position in the detectors in terms of pseudo rapidity. So what I'd recommend is, if you're not familiar with it, just take a look at a quick kind of schematic diagram of the detector, and you can start to try and see what's going on here and make sense of this. But basically, we have the negative pseudo rapidity is in the electron going direction, and the positive pseudo rapidity is going more in the proton going direction. And basically, as we're going to higher pseudo rapidity, such as 4 onwards, we're starting to enter the far forward detector region. So what we're really seeing with this plot is that for our tracks, we see some big dip in efficiency as we kind of transition from the end cap to the far forward region, and then we recover some of that as we actually start to get stuff in the far forward region. But notice that it's much lower efficiency than this region in the middle of kind of -2 to 2, which is our main central detector, basically. And what we saw on the plot before, we looked at, for example, this spike of stuff there, that's basically where our electron end cap is sitting. And from before, we already saw we have a lot of electrons sitting there at the end cap from that plot we made in the second part. So you also see here there's some points of huge error bars. Probably this is telling us basically that in this region, we just don't have much in either case. So when we do the division, it's not particularly accurate. We could rebin this in our plot and make slightly different plots, which for the momentum you might actually want to do to make sense of it. And in particular, you might want to look at different momentum ranges and see what's going on in different regions. So for example, we already know for the scattered electron, primarily we're going to be in one particular region of momentum. So we might want to check, well, for the electrons, or the ones that look like electrons, what's their efficiency as a function of momentum or something like that. Okay, so that's just a kind of quick overview of how we actually get an efficiency. In terms of the task and the exercise, I'll give people 20 minutes or so to work on this. Again, what I'll do is I'll stop sharing so that as I'm moving some stuff around in the background, it's not too distracting. The task is to kind of, let's say, the best bet is probably just pick a favorite Python root or data frames, start from the exercise script, copy that into a file, run it, check you get the output we just saw, and then start to modify it with these extras, which are basically what we're going to try and get is the efficiency as a function of the momentum for the particle. So rather than as a function of pseudo rapidity as we have here, what does that look like as a function of momentum? And if you get that done, also try and, for example, try to plot some 2D correlations. So for example, maybe look at momentum versus eta, pseudo rapidity versus momentum, stuff like that, see what you get and see if you can make sense of that in terms of, again, where these things are and what they look like. What I will do whilst people start to work on that is I'll quickly grab image of the detector region so I can talk some sense about what I just said in terms of the pseudo rapidity. So again, if you have questions or get stuck on anything, please feel free to just mention in the chat or put it in the Mattermost. And if you get a plot out, even just, that first stage, getting that efficiency plot we just saw, if you get that, throw it in the Mattermost, take a look. And if you get an efficiency as a function of momentum, again, put it there and we can take a look at what people have got there as well. So I'm going to stop sharing at this point, and as I say, I'll quickly find an image of the detector. So make sure that and make a bit more sense of it as well. So as people are kind of trying that out and trying to get things going, just as kind of some information as well. So the exercise scripts repository, what I'll do towards the end of next week is I'll add in kind of solutions. We'll see kind of a kind of finished version of this exercise in a second. Still some stuff we could do with it, as we'll see. But that will be uploaded. And also there'll be another live help desk next week. So if you don't have the time or don't get things finished now, but want to keep working on it, no, that's fine. Go away and you can go away and kind of work on things and try it out and try and get something out from it. and come back with questions at that help desk next week as well. If you want to kind of work more on it outside of this. And of course, the recording will be online by then as well. So just a kind of heads up for that. Also to add as well, so the exercise just says, well, find the efficiency as a function of momentum. Um, in the kind of solution to this, I've just done it as the magnitude of the momentum, which is fine. But if you like, you could also do it, for example, as a function of the component of the momentum or something like that. Might be useful to look at. But typically speaking, it's just a case of, you can take that t vector free, the momentum vector, and just say, dot mag, and get the magnitude of that momentum out and use that to fill your plots. So as part of this, one of the things we'll need to do, of course, is add in some new histograms. So you'll probably want to make a histogram of, say, it's the magnitude of the momentum. You'll want to make that and fill it, or say it's the Z, X, Y, whatever your favorite component is. You also need to define and add that. So as something as we're going along, first step would probably be filling a histogram. And one thing you might want to check is just, well, what is a sensible range for filling that? And this is where the power of that T-tree draw command from before is quite useful. We don't need to kind of get everything completely working in the script. We could just say, well, okay, what sort of range does that thing actually have? Go away and draw it in a histogram quickly and see, okay, well, something between this value and this value. Great. I'll then go away and define a histogram with that range and fill it with my plots. Another few minutes to try and work through things. I'll start sharing my screen again in a second or two. I'd maybe just want to show some of the Python script and talk through that just in case anyone is using that or looking at that version of it as well. And also just want to show that it does the same thing, basically, and gives us the same output. And also we'll take a look at kind of the finished version of this before we move on to the last section of this, which starts to look at the kind of full chain analysis as well. Going to go back to sharing my screen now as well. If you're trying to work on something that gets too distracting, just let me know and I can take it away again for another few minutes. But I'm going to quickly kind of show some of the stuff in terms of the addition of this in the finished version in a second, but also just quickly run through the Python version of this as well. Maybe start with that. Take a look at this. Basically, this is what you would get if you just quickly go and grab from the exercise scripts repository, the Python version of this. Very similar sort of setup. You have some input file, in this case, just some string. Output file, which in this case just tells it uses root, says open this file. And then we look at the input file using uproot, and we tell it to turn basically some of the branches there into arrays and then analyze them later on. And also define, again, histograms. So looks very similar to our other script. Semicolons sitting around nowhere. Don't need those in Python land, but go around, define the histograms, and again we have a loop, which overall looks very similar to our other one and all that. It's tabbed correctly because it will complain if not. But again, logic is very much the same. We're looping over all of the events, looping over those stable particles, looping over the thrown particles, picking out the stable ones, checking the PDG code, and filling stuff. So again, a very root sort of way of doing things, but sort of what I'm used to. I'm aware you can kind of, if you made some data frame or some things like that with those arrays, you could do cuts on that directly and stuff like that, and slice them and things. You can do all sorts of fun stuff. I think just in terms of learning it and seeing what's going on, this maybe to me makes more sense. It's a bit more transparent as to what's going on. But if you're already happy with what's going on with those sorts of things in Python, then by all means go ahead. But again, basically we're just defining things, calculating things, filling some histograms, and then unfortunately in this version we have to explicitly actually say which ones we're writing, but whatever. We write our specific files to the histograms to the file, close it, and then our little script's done. And just to prove I'm not making it up, I'm just going to quickly run those and then copy them over. Unfortunately, I can't run them locally because of a Python versioning issue, which is one of the fun things of running with Python, I guess, but it does run in eIC shell, so I'm just going to run it there and copy the result back to my machine in York, and we'll take a look at it. And then we'll take a look at the finished exercise as well. Inverted commas, finished exercise, at least anyway. run those two scripts. I've just done both at once. We'll take a look at the exercise output as well. See, it's got two new files here. Just the output of those, which is some histograms. Copy both. Go through all of the fun of multi-factor authentication. Go, there's our output. It's going to open this. We'll see that's the same as what we had before when we ran. Again, we just have all three plots in our output file. Looks nice and similar. Go and check the numbers match as well if we want. But again, we have the same issue there where we didn't really define the range of this very well, and we have a bunch of stuff bunched up down in this corner here on this particular plot. So we'll take a look at the output for the exercise in a second. We should have a quick look at that first as well. So if you're kind of partway through doing this or have started it and not sure where to go next, as mentioned, the first thing really is just, thinking about it and checking, well, okay, do we have the information we need? The answer in this case, luckily, is yes. Basically, we don't need to get any more information from the tree itself. We already have everything we need in terms of we have the momentum track, we have that Monte Carlo information, we have those reconstruct particle association, stuff like that. We don't actually need anything new as such, but we do need to define some new histograms. So I've defined, in this case, I've also done efficiency as a function of phi, because why not while we're there? I've defined two new plots, which are just the momentum of the thrown charged particles and the momentum of the thrown charged particles which have a matching track. And you can see, in this case, I've given the range of momenta from 0 to 150 in 150 bins. Maybe not exactly a great choice. We'll see. We already know we had things maybe higher energy than that, so we might want to change that. Again, that's why I'm sort of saying it's complete with inverted commas. There's still things we could fix and change in that as well. And I've also assigned some new 2D histograms as well. We see we have the two suggested ones, momentum versus the pseudo rapidity, and also phi versus pseudo rapidity there as well, which we're going to fill. And then finally, we have just some different deltas. So difference in pseudo rapidity, difference in phi between the matched and reconstructed. Again, things what we might want to cut on. Maybe we want things to be within a certain range of the truth, or we actually select them and say that it is a good matched track. And there's also one there in terms of delta P. And then finally, just some histograms for the efficiencies. We can also do 2D efficiencies, again, with that same caveat that we need to make sure the binning is exactly the same as the ones we're dividing. And go ahead and do that and see what we get. So a few extra things to find. And also there's this final bit of the exercise, which was look at just the charged particles. Don't check if they have a matching track, see what you get, and fill some histograms. So that's just those at the end there as well. Main loop is basically the same. We just define some new quantities. Notice this time that we just take, we don't actually bother to assign the momentum to a particular double or anything like that. We just say, okay, fill this new histogram directly with that free vector dot magnitude of it, see what we have, like that. And then equally, we define, though, a bunch of new delta quantities here. We define delta, these different things. Again, we could cut on them if we wanted, something we might want to do, but we don't. We just plot them for now and just fill some histograms with them when they're defined. And again, filling just for the matched tracks, fill the truth value, the momentum or phi or whatever in here as well, such that we can then do that division afterwards. We do now, though, have a new loop, which is just a loop over all the particles, which we do right at the end before we close the loop over all events. So for an event, we do these loops up here first, then do this little one right at the end, and then we close the loop over the events there. And then we do this division of each of them at the end. So general structure the same. This is maybe the only real new sort of sort of bit of logic. But otherwise, it's just a matter of we've defined some new quantities and new histograms, and we've filled them appropriately. And when we run that,
Right. In a while.
takes a little bit of time, a few seconds. We now have a different output file, slightly bigger, probably a good sign. We had some new histograms there. Take a look at that. And what do you know? We have a whole bunch of new histograms in here. So for example, we can look at the momentum for proton charged particles. Again, maybe this isn't actually the best range to choose. We know we have there's protons and stuff like that in there as well. Whether we detect them or have a matching track or not, a different question. But we know we have them to group, so we could maybe change this. Nonetheless, we have what's probably our electrons sitting here, for example, there as well. Other quantities defined, and now, of course, we have all different plots of efficiency as well. So our pseudo rapidity or momentum. Again, a caveat on this, we might actually want to change the range of this. And we know, for example, if that's our electrons, we might want to bin this a bit finer than that and see what's actually happening here. So in terms of an extension to this, you might feasibly say, I want to take a closer look at those, check their electrons. Maybe we could even select out specifically the PTG for the electron, check what's going on with them and bin over a smaller range or different range and look at the efficiency in that particular range. See some sort of thing where it's basically as we kind of get to a certain momentum, it starts to increase, then fall again, but can't really say too much with bins this wide, to be honest. We also have 2D fraction efficiency as well. So here the color scale is basically telling us yellow is very efficient, blue is less efficient. So we see we have pretty good efficiency spread across this region here, both in eta and momentum. And then as we go towards this tail, again, as we get to that region, dipping into the Hall detectors, we have this dip there basically as well. So different way of looking at it, we could also take a look at that as well there. Equally, that's what it just looks like normally in terms of the spread of our particles and stuff like that. So just to kind of emphasize as well, I did run those Python ones, and just to prove that they work exactly the same. Look at that again, we have our different histograms again. You can see, what was that looking at there? Look at the efficiency of our ones, P versus eta. And again, I don't think I have to put side by side to convince you that basically it's exactly the same as what we were just looking at before when we've run the Python version of the script. So it can work in exactly the same way and give us the same result, just up to you which you prefer. What else to say on this? Oh yes, I did promise a quick picture as well. So maybe let's just have that side by side. In terms of our pseudo rapidity, just that plot of eta, I'll put this on the left. I'm going to stick on the right quickly. Somewhat dated plot, I think, but shows the point anyway. We basically have our different regions of the detector, and we can see here drawn lines of the angle theta, the polar angle, and also the pseudo rapidity. We see that basically we have 0 would be the center of the detector, 90 degrees, and we're going more in the electron going direction, we're going more negative, and we see that basically we have this region here, our end cap. What a shock, that's where we're seeing this stuff. And equally the other side, where we're going to very high pseudo rapidities on the other side, we're starting to get stuff in the far forward region. So again, when we had the efficiency, we had this dip, basically, which is showing us this gap effectively where we have some drop in acceptance between the two effectively, is what we're really seeing there basically. So in terms of if you're looking at this and things sort of look strange, or you want to kind of think about it again, kind of it does correspond to some reality. This is after we've passed it through some simulation, we've fed it some particular geometry, and we can take a look and see, okay, does it make sense in terms of what we might expect to see in our detector? In this case, I think it's sort of, we can quite quickly sort of construct a narrative that makes sense, I think, in terms of what we're seeing, which is good. Since an official simulation campaign file, and we'd hope that these DIS events actually correspond to something useful. Okay, so as I said earlier, there is a completely separate version of this, which is looking at the resolution. So again, I don't think we've got time to really go through it too much today, but if you have time between now and next Thursday, where we're going to have the next live help desk, please take a look and start to try and work through it. Have a look through it, and if you've got questions or come across any problems, just drop a message in the Mattermost on the tutorial channel, or kind of come along to the help desk next week and ask about it. And see if you can kind of work through the exercise there, where again, instead of basically looking at the efficiency, we're looking at the resolution of those tracks. Again, basically, how accurately do our matched tracks correspond to the original input? Do we actually reconstruct them with a good accuracy or not, basically, with a decent resolution? So that's the kind of other step for that as well. If you're doing the R data frame version of that, I guess I sort of have to apologize in the sense that, yeah, my experience with data frames was so pleasant that I didn't really feel that I had it in me to immediately go make the resolution version of that as well. But I assume if you're wanting to go that way, you maybe have some experience working with them anyway, to be honest. It's worth a look, even if you're wanting to do the root and Python version, simply because I say it's becoming a bit more common. You might come across analyses that are done this way sometimes. Just to be honest, looking at it from a more Python or root-based background, I find it a bit harder to understand what's going on. We can start to see some of the logic here. For example, we have like a filter here, which is effectively one of our cuts, for example, right? But it's maybe not so obvious how these are then being applied and stuff like that. Okay, so last little session of this is something that has been asked for quite a few times. Unfortunately, not the pod.io. We can also do this. I'll just mention that very briefly, that you can also avoid root entirely, because all of these to some extent are using root, even our data frames, stuff like that. We can completely dodge it. And there's some example cases of that in some slides from Wouter there back in April. Just something to add. If you really hate root and want to look at it in a different way, it's something you can do and approach. No example of it, but just something to be aware of. Okay, but the last bit, though, is something that is asked for quite a bit, and something I've added for this version of the tutorial. So I want to say a few words on this and kind of bring this a bit full circle to get back where we began, where we're talking about the different types of file that are in the simulation campaign. So a question you might very legitimately have is, okay, great. The simulation campaign files are there and there's some reconstructed stuff. But what if I just want to just start from scratch, generate some events, feed them through and get some output? How do I do that? Well, that's what we're going to kind of run through here, where in this very brief section, I'm going to kind of talk you through the kind of 5 steps to getting to where we just were, where we're analyzing some output, basically, some reconstruction output. So one of them we can kind of skip, but I'll touch on that in a second. But in effect, we have 5 steps, one of which I'll only kind of touch on because it really just depends on what you're trying to do. And it really does depend on your particular use case. So I would recommend, if you think this is something you want to do, maybe kind of pause and dive into, for example, Holly's slides from back in April kind of had a nice overview of this in terms of some example cases where, where might you want to start on this chain? There are cases where legitimately you might want to start from the very top. You might want to start by just, I have my event generator, there's no samples that exist. I want to process them and see what happens. And that's fine, that's great. But you might actually have something which jumps in at a different stage, like maybe, you've got something in a simulation campaign, you've run some analysis, but things don't make much sense. So actually need to rewind a step and jump back into the reconstruction and see what's going on there. But at the very basic level, these are all 5 steps where we have some input, some events from your favorite event generator, where you may or may not need to apply beam effects to them, depends upon the particular reaction, depends on the event generator. You then process them through the simulation, pick your favorite detector geometry. Maybe you don't care about some detector region and you just turn it off, which actually I do a lot of the time for my other analysis tasks. And then you want to reconstruct them. You want to look at the clusters of that, the tracks like we've just been looking at, reconstruct some physics quantities and see if we can actually detect the reaction you plugged in at the beginning. And then the final step, of course, the one we just saw, where we're using our little analysis script and processing that in some way. In some cases, you might actually skip the reconstruction and you could just analyze the simulation directly. That might be fine, depends how basic the simulation you want to run is. But at some level, effectively, you have at the very first stage, you need to feed in or generate some events. Could be as simple as just running, and you can actually do this directly, for example, with the simulation step. You could just run some particle gun and say, okay, I want to fire a bunch of pions in this direction from the center of the detector. Or it could be more involved, where you have some particular physics analysis channel, where you say, I want to run this particular physics channel. I want to see if I can analyze it at the eIC. So you take your favorite event generator, a huge list of them. This is not exhaustive. There's many more that are out there that you can use to do this. You can go and run that, get some events, but at the end of the day, it generates basically some text file, which is just going to be event by event, your input particles and your output particles, whether that's a single vertex or multiple vertices or whatever. It's going to be something like that. And basically, to the human eye, these event files are to some extent a bit unreadable, where basically you just have some string of numbers. You can basically just about see in a file. Maybe I'll open one to prove that I'm not lying when I say it's almost incomprehensible. So download one here. I'm going to do this in more because it's a huge file. We have some initialization at the start of it. And then we have basically here, we have an event, which then ends this next one here. So we have a block basically of our events, some initialization stuff. We see this is our input particles, it's an electron and a proton, EP collisions, and then we have some vertex, and then we have a bunch of output particles. In this case, it's a neutron, a pion, and an electron coming out of that as well. But then they have energies, momenta, stuff like that, as you might expect. I say just not exactly the most readable format, given the amount of precision in each of them as well. But once you have that, typically you then apply beam effects, which you do using something called Afterburner. The file I just looked at there, actually, you can already see has had Afterburner applied, and it has different stuff at the top here where it says it's used. It has different conditions, for example, stuff like the crossing angle, the crabbing, and the beam divergence and things like that. So why you need to apply this is simply that in your event generator, if you're just doing this as head-on beams, which are not crabbed and it's just a perfect collision, it doesn't really correspond to what we're actually going to see. Something I would recommend, I would have to go hunting for a presentation where it shows this. A very cool process and very involved process is the fact that when you collide the beams, they're coming in from two different beam pipes, they collide at some angle, and as well as that, to maximize basically how much overlap you have between these beam bunches as they collide, you have to kind of rotate them, something called crabbing, get them to have the largest overlap and get the most collisions basically per crossing there as well. So that's what this crabbing parameter is doing there as well. But they also have divergence in the fact that they're kind of diverging out from the point and stuff like that as well. So lots of parameters, very complicated, an entirely different subset altogether, some nice accelerator physics, but cool stuff. And if you want to take a look at that, I recommend going and find some presentations about this. There's usually some nice diagrams of the crabbing being applied and stuff like that. But nonetheless, it has an impact on the output we get. So when you incorporate all of these things, for example, if you have something which is just going along the direction of the, say, the proton, now they have some crossing angle, it's going to be slightly deflected from that, things like that, right? So these effects do have an impact. They have effects in terms of the transverse momentum of your particles and things like that as well. So you need to apply this typically in terms of looking at your physics events. It's fairly straightforward. If you're in eIC shell like I am now, you can just run abconv, do -h, so you can see what the output of that is. Tells you the different things. Basically, you give it an input file and you tell it what output file you want. And as long as that input file is kind of formatted in a sensible manner, for example, it has a beam energy combination that is kind of recognized, Afterburner will pick that up and identify which configuration to use. You can force it if you want to use different ones using some of these flags. You might want to say, for example, use the high divergence rather than the high acceptance as an example, different configurations, and you might want to double check that between them. Probably more detail than needed, but you can see there's different configurations here, and it will automatically pick up the correct one so long as you're using a kind of typical beam energy, basically. So you can go ahead, plug that in, right? It'll run it, give you an output file. Doesn't really take too long either, to be honest, even for a large number of events. But kind of moving on to kind of the step where I can maybe say a bit more. So of course, I can't really say anything too much about this. That's just going to depend on what you want to simulate. If you want to go and get your particular reaction, just find an event generator that make your events and afterburn them as needed. The main meat though is the simulation step here, where feasibly you say you might want to look at something because the simulation campaign is running, the main detector simulation, where it's using the sort of standard set of detectors as they are at this particular stage. Say though you're doing some work on, clearly this isn't random because this is something I work on, I'm going to say, let's say you're looking at the ZDC, the 0 degree calorimeter in the far forward region, and you really care about some quantities in that detector, and someone else has a new design for the ZDC that you want to stick in and take a look at. That might be a feasible reason why you're going to go and run a simulation using their detector configuration and take a look at it. So to do that, you'd probably need to compile your own version of the detector geometry, but for the purposes of this, we'll pretend that you don't need to. Within the eIC shell, you are going to need to give it some geometry when you run it, though. So we're going to need to source somewhere which has those files. So I'm going to go ahead, prove the point quickly first. Typically, we have some stuff stored in this environment variable detector path. Go ahead and try and look at that. It's not set. It doesn't know what that is, doesn't know what to do with it. But if I source this shell script here, that's basically going to tell it where the detector configuration files are stored. And now if I do that command again, all of a sudden we have all these .xml files. Basically, these are just different detector configurations. So we can see here, for example, that epic crater lake, which going again back full circle at the beginning, where we're seeing when we're looking at these output reconstruction files and simulation campaign, they're kind of organized by the detector configuration and things like that. And what do you know it, that main detector configuration crater lake is sitting there and you can process things there. But as mentioned, you might want to run a specific thing. Maybe you want to run with particular beam energy combination. Basically, it means you have a different field map. Or you maybe only want to run with some Cherenkov and nothing else, stuff like that. There's different configurations here. You can go away and define and make your own and compile it, stuff like that if you need to as well. But basically, once you have that set, we can go ahead and try and run simulation. We can run npsim. We can do -h. As we see, there's a huge list of flags here in terms of things we can specify when we run it. We could, as said, run it with some sort of particle gun if we want as well. But more typically, we're going to run it where we say, okay, I'm going to run this with this compact file. Basically, this is just telling us what detector you want to run, detector configuration. I want to run for some number of events. I want to use this input file. I want to use these events. And I want you to output to this file here. Pretty straightforward. So I'm going to go ahead and do that. It'll take a little bit of time. So if you're doing something similar to this, just be aware it might take a little bit of time. Even 10 events for the full simulation is going to take a couple of minutes. So I'm going to let that run. And it's also going to dump a lot of stuff to screen as it does this, as we'll see in a second. We can suppress that by giving it a different argument as we run it. It's -v flag, stick at the front, which just sets the verbosity level of the output, basically. Yeah, there we go. So lots of stuff being loaded in. So things going on. It's got everything set up. It's happy, and then now hopefully it's going to start running events. As I say, it's going to take a little bit of time, more setup. let that run in the background as I kind of start talking about the next section. You'll see it just ticking along and scrolling through events. You'll see it takes quite a while per event once it actually starts running. A lot of setup first, though. Okay, so once this spits out some output, though, the next thing we might want to do, I'll say this may be enough, maybe if you're just simulating a detector. So for example, in my other hat, when I'm not looking at some physics analysis, I'm looking at detector design. A lot of the time, I'm changing the geometry of pair spectrometer for the luminosity monitoring. And to be honest, all we're looking at is you're looking at electron hits in that, and you have an electron hit at a time. It doesn't really need particularly sophisticated clustering or anything like that, reconstruction. So even at a Geant 4 kind of output level, a simulation output level, you can just look at it and say, all right, for this event, sum all of the energy there, and that's my hit in this detector. You can just do stuff like that quite straightforwardly for a sort of low-level analysis of it. Very coarse, very crude, but for the purposes we need for sort of a quick simulation and quick check, it works. For more complicated stuff, you might want to actually start doing, for example, if you're firing two things at the same time, you're going to start wanting to do cluster matching and stuff like that, cluster reconstruction, which you need a reconstruction algorithm for. So there we go, that's run. And that reconstruction comes in through eIC Recon in this step. Again, if you're in the eIC shell, this is installed by default. So if I again do just eIC Recon -H, it's going to run it and tell us what kind of arguments we can give for it. Luckily, it doesn't fill the entire screen this time. A relatively slimline list of different options. We can run it with specific plugins if we want, stuff like that, different configs, things like this. But typically, again, we're just going to be telling it, run the reconstruction, run it on this file, output this file, and this is the detector geometry you should use to kind of do the reconstruction. Again, that matters because it's going to need to know things like the field in certain regions. So for example, if you're looking at the far forward region, if you have charged particles there, what's going to happen to them is going to vastly differ depending upon the field configuration in that region. So you'd need to know that and feed that in. So again, it can take a very long time, but the sort of command is going to look pretty straightforward. Basically, we just tell it eIC Recon or pod.io. Basically, it's just our file we got before. I want something called this, eIC Recon out.root. Process this many events, use this XML file, and this is the simulation file I want you to process. So in this case, just saying sim output is the thing I've got from the simulation before. So I've modified it, following up on that one I just ran. I'm going to go ahead, run that, and we'll get some reconstructed file from the thing we just simulated. So our 10 events, we're going to process them through, and we're going to tell it that we use the particular configuration. Notice we use the 5 and 41 configuration and stuff like that there, not the main Crater Lake one. Okay, so that's all great. But in reality, you say if you were doing this from scratch, even if it was a case of you have your event generation file and you want to then afterburn it, simulate it, and then reconstruct it, you probably don't want to sit there and run the series of commands sequentially yourself. So it's probably going to be easier to just stick all of this in some sort of bash script, to be honest, where we can just run these sequentially bit by bit. I've got a script here I'm going to run, show you that we've got some output there. So simulation output and our reconstruction output. But I'm also just going to run bash script I made, which is just the one on the right, which is going to run the commands we've just done. It's going to basically source the detector files, so it knows where detector output is. I'm sorry, detector path is. It's going to run the simulation. It's going to wait 3 seconds, and then it's going to run the reconstruction afterwards as well, and it's going to exit. So, great, that saves us typing 2 commands. Very basic, very straightforward. We haven't given it any arguments, but you could quickly see that, for example, you could change this with take some input arguments, which are just like a naming convention. So say you're sequentially running over a bunch of files, you just give it a naming convention, and it will then maybe automatically generate the output and stuff like that. I have some examples of that, which are linked below, if you want to take a closer look at them. And you could then just run that and say, okay, run it for file 1 for 1,000 events or something. Maybe those are your arguments you put in. Go ahead and run that. But that's nice kind of on its own, but maybe not that realistic. As we're kind of seeing as this thing kind of crunches away on the left, it takes a long time. It takes a very long time if we want to run the full simulation, run the reconstruction. So realistically, you're probably not going to sit and interactively run 1,000 events through something like this. So the power of having some little shell script which would do all of the different commands we need is that we could quite quickly and easily make a compute job which just says, okay, for example, something like Slurm or Swift, which get used on compute clusters, makes a little job which just says, run this script with these arguments. And again, if we had it set up just that it has these input arguments, we can just say, okay, as some compute job, just request these resources and run this script with those things there as well. So we can easily do that. But there's a kind of, I'll maybe leave people, if this is something you want to do, I'll leave it to people to read through this. Quite a few different considerations as we're doing this, namely that, as we've seen here, all of this is in the EIC shell. Some environments let you just say, use this container and run this command, stuff like that. And we also want to make sure that this is a pretty straightforward and simple job. Just, execute some command with arguments. Try to keep it nice and simple. So the script we've just made would be a nice candidate, and we could quite easily kind of work with that. What would be nicer, though, a lot of the time as well, is that that one we're running now relies on us being inside EIC shell. So if I run that outside, it has no idea what these things are, doesn't know what npsim is, doesn't know what EIC recon is. But we could make a script which basically runs the EIC shell, and once it's run it, execute the script we just did. So I've done that, and I'm also, I am cheating a little bit in this. We need to be a bit careful of this because of paths like that, detect a path. It might be set at a time that's not exactly where you think. So my script here is saying, okay, load EIC shell, and then when you're in there, execute this script, which did all those steps above. So I'm going to set that off again. It'll sit there and do all of those things as we kind of tick along there as well. So very nice, and it's basically something like that we could put in a compute job and run. Quite a lot of other stuff we'd want to do. I have some examples of that from the JLab form you can take a look at. So there's basically the kind of job you'd submit, and also a script which then submits a lot of jobs basically as well. So this one is what it would run. This one is the job which is the script which actually makes the job and submits it, telling it to run the other thing basically. So feel free to kind of take them as a template if you want to take a look. But please kind of keep these things in mind above and follow the same sort of rules as doing anything with these sort of compute clusters. Check your scripts run interactively first. Check a small test job first. Don't just, go, great, it works interactively. Let's now do 1,000 jobs of 1,000,000 events each and then crash the whole system or anything like that, right? Keep it small scale, simple at first, and keep in mind it's a kind of shared and finite resource in a lot of cases. Just make sure it's kind of by the book, basically. And I'm not just saying this disclaimer so I get blamed for a bunch of people crashing a bunch of forms all over the world. It's just kind of good practice generally. And also keep in mind that some of the things I'm saying, like this, apparently is strongly not recommended for use at BNL when you're using, I think it's Condor's the system there. So kind of keep that in mind. There's a link to a discussion on Mattermost about this as well. So if you want to read more, if it's relevant to you there, take a look. Now have a look at that as well. And I guess, I don't know why it's sounding like I'm turning it like a data talk, basically, where I'm just ending with a bunch of warnings and disclaimers. As a really big disclaimer, I know this section of the tutorial has been kind of asked for a lot, where it's like, oh, I want to see a kind of, start to finish full chain thing, how do I do this? My strong recommendation would be to go back to the top of this page and go to that presentation Holly did at CERN, take a look at it and really think about what you actually need to do and at which step you actually need to start this. It might not be the case that you need to kind of actually go back and re-simulate everything, for example. Maybe you just want to change some parameters into reconstruction and redo the reconstruction, but the simulation and the geometry itself is fine. You just need other stuff to do as well. So there's sometimes good reasons why you shouldn't really be doing this from scratch, not least that, as we're seeing here on the left, it's quite computationally intensive. And also it's very prone to, if you're going away and doing this kind of on your own, for example, starting from scratch, working through all of this stuff, you can very easily run into a situation where maybe you see some error in your code or in your output, which actually just corresponds to something where the version you're using is not the version that's now being used in the simulation campaign, and people don't see it when they're running those files. So it's very much not as reproducible for that reason to some extent. So when you're doing this, keep that in mind and keep track of that. If there's something you think, okay, this is definitely what I want to do, and this is definitely what the approach I want to take, just think carefully about that and bring this full circle, and back to where we started, where possible, if you do want to start from scratch and work through this, what you should really be doing is thinking, well, okay, is there a way in which I can generate some event sample, and get it added to the production campaigns in some way, even if it's just a small sample or something like that, and bring that discussion as to, you don't need a lot of resources. You just want to run just a small job on the side of this as we go along, stuff like that. Because once it's in there and it's in that official campaign, at least it's then more reproducible. People can go look at it, look at the version that's used for it, and try and see what's going wrong if something is going wrong. But this is kind of there just to maybe give you an idea of the steps that were involved in that and how we got to what we were looking at to begin with. And there may well be a very legitimate case where you want to go away and do this, and simulate things yourself, reconstruct them yourself. Actually doing a lot of that is very much the topic of other tutorials though. So for example, if you want to go and change the geometry, I'd recommend go back to the start at the setup, and introduction slides. There was a link to the geometry tutorial, and also there's a tutorial on reconstruction algorithms. And actually that's something we're going to be following up on, I believe in November is the plan for that. We'll have another tutorial on reconstruction algorithms. Okay, so that basically brings us to the end. Slightly less over time this morning, so just a minute over time. One thing I would say is that this last slide is really just saying, take a look at the kind of extras here. There's an examples repository, which hopefully we'll be getting more and more fleshed in as we go along. And there's also a kind of exercise scripts directory, which we looked at earlier to get just sort of the skeletons. And after the live help desk next week, I'll add the completed versions of the scripts there as well. Although as we've seen, there's still stuff you could play around to do with them as well. So they'll be there and added to that same tab once they're there as well. So check them out and have a look. And as a closing remark, I guess, yeah, please do just, I know it's kind of 2 hours, but also, it's a lot to kind of process and do. Take a look at the exercise again, try and do some of the stuff. And if you get things, just post it in the Mattermost, ask questions. And if you're just getting started, talk to your working groups, what kind of physics are involved in, chat to people. People have examples of different bits and pieces and in terms of how to do things. And you can kind of try and get involved and see what's going on, how people are doing things that way as well. So that brings us to the end of the day. And here in Britain, it's 6 o'clock, which for me means it's time for some light refreshment somewhere. So thank you for joining today. And if you have any questions or anything to follow up on, please just say Mattermost is there, and the live help desk will be there again, same time as the tutorial today, next week. Right, thanks everyone. Have a good rest of the day, or good evening, wherever you are.